So good afternoon, everyone. So yesterday we just started the topic of atomic structure. We'll continue with the same. And I'll just quickly go through Rutherford experiment. What was the inference we could have drawn from Rutherford experiment? See, if we just look at broadly, what we notice here, see, if we bombard or if we make a fast-moving alpha particle strike a gold foil, if it was homogeneous mass, like a sheet of paper, would have expected all these alpha particles to have a similar behavior. But what we find, the behavior of alpha particles are different, and very small number of alpha particles, in fact, bounced back. So at first thing, it indicates this whole mass is not homogeneous. It's not something that electron and proton, everything is distributed uniformly over the volume of the sheet. And since the number of alpha particles which rebounded were very small fraction, it indicated this, the one which bounced back, it encountered something very different from rest of the alpha particle. And if you mathematical model, if you put whole thing in terms of mathematical modeling, see what we find here. So this is something based on the angle at which it deviated, proportion of alpha particles which retraces path. He could figure out what the distribution of charge has to be, and based on that arrangement, is his calculation, if we came to an understanding that atom also is somewhat similar to solar system, lot of empty space, and similar to solar system, at the center you have the sun, and different planets are going around. Here also there's a nucleus, and in solar system, gravitation force makes planet to go them around the sun in circular motion. Here it is electrostatic force between nucleus and the electron. But there's a key difference here. Unlike gravitation system, in case of gravitation system, all planets have different mass and they can have any value of radius. Here all electrons have exactly the same mass and same charge. But yes, in a way it is similar. There's a lot of empty space, and the nucleus around which electrons go around occupy a very small fraction of volume. Okay? That's all we need to know, and we just briefly discuss, and these two are also minor points. We discuss something about impact parameter. So suppose this alpha particle, impact parameter is a perpendicular distance of velocity from the center of nucleus. This becomes impact parameter, and only thing we need to understand is the angle of deviation each alpha particle will suffer will depend on B. Higher the value of B is, lesser the deviation it will suffer. And the one which will retrace its path, one which will have an angle of deviation as 180 degree, will have impact parameter of 0. Okay, sir. And the one which has impact parameter of 0, it will retrace its path. It will basically something, and so it will have a minimum distance of approach or closest approach, and this we can find out based on conservation of energy. That's what only the equation you can form. Rest all qualitative. Only one mathematical equation which can form is this. Then we came to Bohr model. Bohr's model, what are things we need to keep in mind? See, this is said that there are only certain orbits which are permissible. I say this something in very simple terms. This was the Bohr's equation, Bohr's postulate, and Bohr's law. It said MRV is equal to NH by 2 pi. And this term is we can also call MRV is nothing but angular momentum of orbiting electron. And angular momentum is equal to NH into 2 pi, N is an integer. So we can say angular momentum of orbiting electrons in hydrogen-like atom is integral multiple of h by 2 pi. It could be 1, 2, 3, and those integral multiple, when it is n is equal to 1, it is called first orbit, second orbit, and third orbit. So that's an additional condition he imposed, in addition to normal condition for circular motion. In case of circular motion, centripetal force has to be equal to electrostatic force of attraction. So just look at this. So if here there are two terms, N and Z. Moment, what does Z define here? Z defines this is something, this identifies the atom, and N defines the orbit. So if I say if Z is equal to 2 and N is equal to 4, What does z is equal to 2 and n is equal to 4 mean? Jaideep, can you tell me if I write z is equal to n is equal to 4, what does this imply?
It's the fourth orbit and the atom consists of 2 protons.
2 protons. Perfect. So this is the thing. This is for, so it will give you what is the, yes, fourth orbit of which one? Z is equal to 2. It has 2 protons, but since it has to be similar to hydrogen atom, it cannot contain 2 electrons. So we write something like this. So Z is equal to 2, N is equal to 4. So moment we define this, just a second, I just take a look. Hello? Hello? Yes? No, not interested. Thank you. Okay. So moment these two equations, so if we substitute any value of z and n, any value of z and n, I can find out for any combination of z and n, there's a particular value of r and v. Particular value of r, v for any combination of hydrogen-like atom. For any particular orbit, there's a unique value of radius and unique value of velocity. You will have multiple numbers. So you understand from these two equations that when we substitute any particular atom number, atomic number and orbital number, I have two equations of radius and velocity. I can find a unique value of radius and unique value of velocity. So if I substitute z is equal to 2, n is equal to 4, if I get the value of r, it will be the orbital radius of electron in the fourth orbit in helium ion. And V will give you the velocity of that orbiting electron. So you understand these two equations, and they're very simple things. You understand Z is equal to 1, N is equal to 1 imply first orbit of hydrogen atom. So it gives you a unique value of R and V for each Z and N combination. And I hope this point is all of you are understood. Okay, and it is something similar to this. So suppose from this equation, if we have to find radius, what is the orbital radius for any combination of Z and N? To obtain radius, we eliminate V. That's what we had done yesterday. And if we eliminate V from one equation, substitute into other, this is the expression of radius we get here. And this expression, you know, which are the terms which are variable here? N term will depend on the N and Z are something which are not fixed. The rest are like a constant. If you put those values and convert into a particular unit, R comes equal to 0.53 N square by Z Armstrong. Okay. So what we understand from this equation, I think 2-3 things we can understand. One thing we can understand, radius varies as N square by, I have written M also, but M is something we can skip. I'll come some question, M becomes useful. R is proportional to N square by Z. So what does it imply? So, so if I take R naught, what is R naught here? If I define R naught is corresponding to N is equal to 1 and Z is equal to 1, which is called Bohr's radius. Bohr's radius is equal to 53 Armstrong. So if first orbital radius of hydrogen atom is 53 Armstrong, what is the radius of second orbital of hydrogen atom? The second atom, N will become 2, it will become 4 times. It will become equal to 5.53 into 4. Similar way, if I have to ask you, how do you find the orbital radius of something like this? What does this mean? From this, can I find, sorry, not orbital, what is the orbital radius of electron in the fourth orbit of helium atom? Can I find from this here? You can easily find. You can substitute this term. So this expression helps me find orbital radius of any electron for any hydrogen-like atom. So this is something, this is pretty simple substitution. Let's understand what this expression implies. And sometimes more useful term is R is proportional to N square by Z. And M also, if we can remember, is better. What is radius of fourth orbit? First, we can easily calculate. What is radius of third orbit of ionized lithium ion? Can we calculate this one? So what do we substitute N as? In this case, since N orbit, third orbit, I'll substitute N is equal to 3 in this above equation. And since it's a lithium, double ionized lithium, I'll substitute Z is equal to 3. If you substitute this value, find the radius. So that's as simple as that. So finding radius is simple. Okay. So what we understood from this expression, see, most of the terms, we can easily find the radius of first orbit of hydrogen atom. We can find out velocity of orbiting electron in the first orbit of hydrogen atom. And we can also find energy of electron in the first orbit of hydrogen atom. And thus we can use as a reference. So if we, with reference to these values, we can find corresponding value of radius and energy for any atom for any orbit. That's our understanding. This is what many problems involve. So we can find R, V, or energy value for any hydrogen-like atom for any orbit with reference to radius and energy. Typically, velocity not so common, even velocity also. So with reference to radius, velocity, and energy of electron in the first orbit of hydrogen atom, we can find corresponding value for any other atom, all these terms. And that's what we'll see in some of the examples what we do today. Okay, so considering further, similar with the way you can find R, we can, once we find the R, we can find velocity also. Velocity expression comes something like this, which is simplified. This is the term what we get for velocity. And here also what we notice, velocity is proportional to Z by N. So that is something we keep in mind. Okay, so what does it indicate? It's proportional to 1 by N. So compared to orbital velocity of electron in the first orbit of hydrogen. If you go to second orbit, N becomes 2, velocity becomes half. So orbiting velocity in the second orbit is half of the orbiting velocity in the first orbit. N becomes 3, third orbit, velocity becomes 1/3, or kinetic energy becomes 1/9. That's what this equation indicates. And similar to if I compare first orbit of hydrogen atom vis-a-vis first orbit of helium ion, what is the, how would velocity compare? If I compare N is equal to 1 for hydrogen atom and first orbit of helium ion, first orbit, how would velocity compare? So what we notice here is since V is proportional to Z and this is 2, first orbit velocity in case of helium is twice as much. And since the velocity is twice as much, first orbit electron energy, velocity is twice as much, kinetic energy will be 4 times, and total energy also is equal to kinetic energy but negative in sign. Hence total energy also will be negative 4 times of energy in hydrogen atom. Is this understood so far, Karthikeya?
Yes, sir.
Have you understood so far? It is clear how to, can you quickly work it out in your mind what we are saying here?
Yes, sir.
Okay, and this is what is proportions are pretty useful. If you understand proportion, from if I know V is proportional to Z by N, what would kinetic energy be proportional to, Karthikeya? I'm expressing everything in terms of Z and N because these are the two key variables here. So if V is proportional to Z by N, what would kinetic energy be proportional to, Karthikeya?
Z square by N square.
Z square by N square. And if kinetic energy is proportional to Z square by N square, what would total energy be proportional to?
It will be proportional to minus of Z square by N square.
Minus, but still in terms of proportion it will cancel out. And when you take the ratio, it will still be equal to Z square by N square.
Yes, sir.
When ratio will cancel out. So these are two things what we have. So to summarize what we said, R is proportional to N square by Z and V is proportional to Z by N. Based on this, we can find most of the terms, and that's what we'll use. Okay, and so we have found R, we have found V. How do you find energy? We can find energy in 2 ways. Energy, total energy. One way of finding total energy is equal to half of potential energy. Okay, the total energy, half of the potential energy. So I can find in terms of potential energy, or what is the total energy is equal to negative of kinetic energy. So any of the two methods we can substitute and we can find the expression of energy. And this energy also in simple terms, again in terms of Z and N, I can write energy is equal to minus 13.6 Z square by N square in terms of electron volts. And this term is also called Rydberg constant. Rydberg constant, there are two constants, one is terms of wavelength, other is terms of energy. So here the Rydberg constant is 13.6. And okay, so this expression, I think this is third formula what we need to remember. And from here we can find out, once I have this expression, for any hydrogen-like atom, for any orbit, we can calculate what is the total energy, what is the kinetic energy, and what is the potential energy. Suppose from this, if I ask you, what is the potential energy of electron in hydrogen atom in third orbit? Can we tell what is the expression will be? What we need to do? Can we find potential energy of electron in hydrogen atom in the third orbit? I'm not asking total energy. Now I'm asking potential energy. How is potential energy related to total energy? Potential energy is twice of total energy. The potential energy will be equal to, so I can calculate first total energy. If I multiply total energy by 2, I'll get the potential energy. And that's a figure you should remember here. And it's not too difficult to understand. So I can calculate what will be the total energy. Total energy I can easily calculate by its hydrogen atom. I'll substitute Z is equal to 1. I'll substitute N is equal to 3. So the total energy, if I have to calculate potential energy, it will be equal to minus 13.6 into 1 square divided by 3 square, whole thing multiplied by 2. So from this expression, what we understand here, what we should know, if I know this expression, I can calculate potential energy, total energy, as well as kinetic energy for any hydrogen-like atom for any orbit. For atomic number, I substitute here. Orbital number I substitute here. And depending on what I need to calculate, if I need to calculate kinetic energy, this sign becomes plus. If I had to calculate total energy, if I had to calculate potential energy, I multiply by 2. So that's why we can calculate all. So what we have done, so with we can, if we know the radius of what you call Bohr's radius, I can calculate the radius also. We can calculate velocity also, and we can calculate energy also. All with respect to, we can calculate with respect to electron in the ground state of hydrogen atom. And what is electronic transition? This is also something, if you look at, we should be familiar with. So first thing what it says, electrons, see, for if we take a particular atom, let's say take a hydrogen atom. The hydrogen atom, moment you take hydrogen atom, Z becomes equal to 1. Number of protons becomes equal to 1. Now other variable is N. So when we substitute N is equal to 1, I'll get a particular value of R and I get a particular value of B, I get a particular value of energy. So that gives me what is the, so if I substitute N is equal to 1 and Z is equal to 1 in those two equations, I get the value of radius, I get the velocity, I get the energy. Similarly, I substitute N is equal to 2, I get the radius, velocity and energy. So what you notice here, so what it says, it can move only in these orbits corresponding to N is equal to 1, 2, 3, 4, 5. Electron cannot move in an orbit which is somewhere in between. And since it cannot, and its energy is related to radius, since the radius is defined, even energy also is defined. It can have energy corresponding to N is equal to 1, it can have energy corresponding to 2, energy corresponding to 3. It cannot have energy anything in between. So energies are quantized. Energies are quantized. So this is something, and typically, and where is the energy lowest level? Nearer to the, see, in case of, you just imagine in case of Earth also, which satellite will have lowest energy? The which has lowest orbital radius. Higher the orbital radius, greater is the energy level. We have to give more energy for satellite to go around in a higher radius. Similar thing happens here also. This will be the lowest energy state. If we add some more energy, it will go to next higher state. If we add exactly this amount of energy corresponding to difference between the two, it will go to N is equal to 3 and corresponding. So electrons, typically when we say in the ground state, we are talking about hydrogen-like atoms. There's only one electron. How many electrons are orbiting? Only one electron. This model is only for single electron hydrogen-like atom. So only one electron is orbiting. And in natural state, it's called ground state. Typically, it will be in N is equal to 1, lowest energy state. What does ionization energy mean? Ionization energy is something similar to escape velocity. And this ionization energy is amount of energy which need to be given so that it may escape nucleus pull. This nucleus is exerting a pulling force to make electron escape the attractive pull from the nucleus. So where it has to reach to escape attractive pull, it has to reach infinity. So what is the ionization energy? Most of you will be familiar with. When it reaches infinity, we can say that orbital number is equal to infinity. So it has to, from this state, from N is equal to 1, it has to reach N is equal to infinity. So energy required to transition an electron from N is equal to 1 to N is equal to infinity is called ionization energy. When it reaches N is equal to infinity, it means it's no longer attached to the nucleus. It becomes a free electron. Ionization energy. So this energy is, what is the energy required here? This is equal to final energy minus the initial total energy, E infinity minus En, and energy is proportional to n, 1 by n square. When n becomes infinity, this energy term is equal to 0. Okay, so what is the ionization energy required? Ionization is equal to minus En, and En itself is negative. Hence, the overall ionization energy is positive. So if I ask you, what is the ionization energy required for hydrogen atom when electron is in the ground state? How much energy is required? What is the ionization energy required? Shreya? Electron in the ground state of hydrogen, what is energy required? What is ionization energy required?
En.
En is how much? In En is equal to 1. So what is E equal to? Say En. En is equal to what? In case of En is equal to minus 13.6 Z square by N square. So for hydrogen atom, if it is in the ground state, N is equal to 1, En is equal to minus 13.6. So what is the energy required? What is the ionization energy for electron in the ground state? Energy ionization is equal to 13.6 electron volts. Okay, so and if it is N is equal to 2, so when N is equal to 2 means what? When we say N is equal to 2, it is first excited state. So first excited state, N is equal to 2 is the first excited state, N is equal to 3 is called second excited state. Or we can say in the second orbital, the second orbital is first excited state, third orbital is second excited state, so and so on and so forth. So this is ground state, first excited state, second excited state, and so on and so forth. So ionization energy is equal to the is negative of total energy in the ground state. Ionization energy is equal to negative of total energy in the ground state. And this also is similar to, again, if you try to recall, it's something similar to gravitation. What is the kinetic energy need to be given to an object on the Earth's surface? The kinetic energy need to be given is equal to, in terms of magnitude, is equal to potential energy there also. For electron in the ground state, H is equal to energy is ionization energy is 13.6. Okay, and if ionization energy for electron in hydrogen atom is 13.6, what will be the corresponding ionization energy in case of helium ion? What will be the ionization energy in case of helium ion? Kaushik, what will be the ionization energy in case of helium ion?
54.4.
Why?
Like
I have written that one. Can you tell me why?
So because Z is 2.
Z is 2.
1.
N is equal to 1. And so basically it becomes 4 times. And similar way, since you have done that one, can you also tell me what will be the ionization energy for double ionized lithium ion
In the ground state, so
in from the ground state?
N is 1 and Z is 3.
Z is 3. And so it will become 9 times of 13.6. Easy calculate. So suppose I calculate what is the ionization energy required from lithium ion from N is equal to 2. Can you also do that? You can easily calculate what is the energy in lithium, the doubly ionized lithium and N is equal to 2. I'll calculate the total energy. Total energy minus 13.6 into Z square is equal to 3 square divided by N square by 4. This is the energy in the ground state. It has negative energy. So energy, extra energy need to be supplied to ionize it. Is this energy which need to be supplied? For any orbital, for any hydrogen atom, we can calculate ionization energy. Khyati, can you calculate ionization energy for any value of Z, any value of N?
Yes, sir.
No problems. Okay, so ionization energy is easy to calculate, and ionization energy need not be from the ground level. It can also be from, if it is already in the excited state, it will release lesser energy. So we can easily calculate ionization energy. And then we call out one more similar term. Another similar term is excitation energy. So excitation energy, if we take up excitation energy, is energy required to enable electron to jump to a higher orbit. So what is excitation energy? Minimum excitation energy required. If electron is here, next higher orbit is this. This is the minimum energy need to be supplied for it to jump to the next higher orbit. So this is something, it is jumping from where to, from 1 to 2. Similarly, if we have to jump to, if we supply more energy, it may jump into not to the second, it may jump to third orbit. So this is something, so to make it move from one lower orbit to higher orbit, is called excitation energy. And minimum excitation energy from the ground state is corresponding to from n is equal to 1 to n is equal to 2. That we'll see that, and excitation energy. So except and as soon as what we say here, and how when we talk about absorption of energy, what does this term mean? Let's try and understand. I think we'll come to next slide. We'll come to that time also. What we notice here, see, typically, if we take a hydrogen atom, electron will be in the ground state. If we give energy to its electron, it moves to a higher orbit, but it doesn't remain in the higher orbit. As soon as it reaches a higher orbit, again it comes back to lower its ground state, either in single step or multiple step. When it comes, it loses energy. So to first it has to receive energy to get excited, and after it gets excited, it comes back to ground state in single step or multiple step by emitting energy. And when you emit energy, it emits energy in form of EM radiation. So where do we get emission? Emission is due to what causes emission? Transition of electron from higher orbit to lower orbit leads to emission, and absorption of energy leads to excitation of electron. Absorption of energy leads to excitation, and from excited state it comes back to lower state by emitting energy equivalent to energy gap. Yes, Vignesh, any query?
Yes, sir. So, like, why can't the electron stay in the same orbit when it has the sufficient energy to, like,
This is
change
lazy. That is something you don't think that you are the only one who is lazy. Okay. See, anything, just think of anything, any object you talk about, whenever we talk of potential energy, any object tends to go to a state which is in the lowest energy form. So if a lower energy state is possible, all and everything, every nature, that's a law of nature. It tends to gravitate towards lowest energy state. Okay, so that's a natural property. So if a lower energy state is possible, unless something is preventing it. See, in case of, see, we can think of this, even bowl also. When we keep a smooth bowl, if I place an object here, where it comes down, finally settle down to this level. Why does it settle down
Yes,
to this
sir.
level? The lowest energy state. So something similar happens here, not only in this process, every process will find if a lower energy state is possible, it will always try to achieve lowest possible energy state. See, it is lazy, but you know, in laziness is very quick. See, can you be lazy and be quick? Yes, it's possible. So what it does, it comes back to lower energy state, but it doesn't come it lazily. It comes very quickly. So as soon as it gets excited, within not even nanometer, actually it's much less than that. Within nanosecond, it comes back to normal state. So it doesn't, in natural state, unless there's some way we prevent its transition from higher energy to lower energy state, it comes back very quickly in the time much less than nanoseconds. And when it comes back, since there's a difference in energy level, and we know the energy cannot be created or destroyed, electron is losing energy. So the loss of energy has to go somewhere. That energy comes in form of EM radiation. So EM waves emitted when it moves from higher energy to lower energy state, and that energy emitted is equal to delta is emission of energy. And what we notice here, since energy states are well defined, hence emission spectrum of any atom also is well defined. We do not get random energy photon, we get photon. So when you get photon, photon may have energy equivalent to this. Photon may have energy equivalent to this. Photon cannot have energy level which is something like this. So photon energy will always correspond to delta E corresponding to two states. Okay, and I think that's the way whole atomic structure was arrived at, by observation of emission spectrum and absorption spectrum. How do you get absorption spectrum? I think I mentioned sometime earlier. Can someone tell me how do we obtain absorption spectrum? So suppose I want to get what is the emission spectrum and what is the absorption spectrum. How would I obtain that one? Can you think of what kind of experiment we can conduct to obtain absorption spectrum? I mentioned sometimes, you suppose it's some space. What does absorption spectrum mean? If I have space which contains hydrogen atoms, and if we have EM radiation, which has all energy state, and it has energy state right from 0 electron volt to say about it has 15 electron volts. If we pass all this radiation and we check what is the radiation we receive here. When we receive, we find some of the radiation which were absent from here, which has passed through hydrogen. Some radiations are missing, some energy states are missing, certain wavelengths are missing. Which wavelengths are missing, why they are missing, that has been absorbed by hydrogen atom. So when we observe this, this called absorption spectrum, which are the one which are missing, which have been absorbed by hydrogen atom. So if rays are passed like this, suppose a light travels a straight path, light goes like this, I observe it here. What is emission spectrum? So suppose I keep an instrument which observes radiation. I'll observe, even though there's no light traveling this, I'll observe some EM waves reaching here. Which EM waves will reach here? These are the EM waves which have been emitted by hydrogen atom. So there's absorption. So when we make radiation of a range of energy or radiation of range of wavelength pass through an atom, we find certain wavelengths get absorbed and rest of the wavelengths are not absorbed at all. Which wavelength gets absorbed, that will give you absorption spectrum. And similar way, the radiation here, this radiation, if I keep a telescope and observe here, there's no light here. Whatever is coming here is because of radiation from the hydrogen atom. And these radiation are nothing but emission spectrum. And emission spectrum will, so I hope you understand what is absorption spectrum, what is emission spectrum. If it is in form of radiation, so we know if we have EM radiation of different energy level, it means there are several photons of different energy level. And when this photon get absorbed means what? Photon will get absorbed. Whenever a photon gets absorbed, it will transfer its entire energy. Part energy transfer is not possible. So only those photons which have energy level exactly matching the energy gap here will get absorbed, which are not exactly matching will not get absorbed. And after they get absorbed, again, this suppose depending on what is the energy of a photon was, it may get excited to this level, or this level. And after get excited, it will come back to the same level by emitting radiation. Thus, absorption spectrum and emission spectrum. And emission spectrum is something like this. What is emission? It moves from higher energy level to lower energy level. Then suppose an electron is, and how do we calculate? So let's look at that. So first, what is written here? So this is for hydrogen atom. This is the ground state corresponding to n is equal to 1. Energy is equal to 13.6. This is the energy of electron. Actually, it's electron nucleus combination because nucleus is not changing. We assign the entire energy to electron only. So this is ground state, and this is the first excited state. N is equal to 2 is first excited state. We calculate energy by dividing by 13.6 by 4. It is minus 3.4. This is N is equal to 3 or second excited state. And this is third excited state means N is equal to 4. So any excited state, the N number will be one number higher. So this is 13.6. This is N is equal to 3. So 13.6 by 9. And this will be 13.6 by 16 and 13.6 by 25. So we get these numbers. So suppose, okay, and suppose what has to be energy of photon for electron to get excited to N is equal to 4? How would electron in hydrogen atom will get excited to N is equal to 4? What is the energy of photon we need? N is equal to 4. So what has to happen? The electron has moved from here to here to here to here. So it has gained so much of energy. So what has to be energy of photon? This photon energy has to be exactly equal to this energy gap. And how much is this energy gap? This minus this in energy gap. So N is equal to 4 to make an electron to go to state, third excited state, or N is equal to 4. Energy required is E4 minus E1. That's the energy which need to be given. That's the energy the photon must have. What is E4 minus E1? Minus 8.85 minus 13.6. So that is roughly about 12.75 electron volts. So if we make EM radiation having energy exactly equal to this pass through hydrogen atom, we'll find quite a few photons will be missing. Quite a photons will get absorbed by the hydrogen atom. So it goes to that one. And soon after absorption, what will happen? The one which has gone into n is equal to 4, it will come back to the ground state. How many different ways? So let's first understand emission spectrum. What is the energy of emitted radiation? Energy of emitted radiation is nothing but loss of energy between two states. When we are talking about loss, see, typically when we talk about delta is final value minus initial value. But when we say loss, we use the term loss when initial value is greater than the final value. So when we talk loss, we reverse our sign. Loss is equal to initial energy minus the final energy. Keep this in mind. Delta is equal to final value minus initial value. But in case of loss, loss itself implies that final value is less than initial value. It is initial minus final, reverse direction. So if I write delta E, so it is moving from initial state. What is the energy in the initial state? N is equal to N initial. This is energy in the initial state. Initial, this is the initial principal quantum number. So N is Ni, it jumps to Nf. So this is delta E, and if I rearrange, this term comes something like this. So if, so let's say if I is equal to 5 and final is equal to 2, what does it mean? And Z is equal to 1. What does it mean? So this gives you delta E. This will give you energy of radiation when an electron in hydrogen atom drops from n is equal to 5 or fifth orbit to second orbit. It will give the energy state. Are you clear? So this is something. So if I say, so suppose I say, well, what is the, suppose we calculate, okay. So similar way, let's take one example here. Pritam?
Yes, sir.
Suppose I say this hydrogen atom, can we calculate what will be the energy of emission spectrum corresponding to this transition? Do you understand what is this transition mean? This line here?
Yes, sir.
This transition from which state to which state?
N is equal to 4 to N is equal to 2.
No, it's from fourth orbit to second orbit. We can also define in terms of excited state. I can say from third excited state to first excited state. Can we calculate what will be the energy of radiation emitted when an electron transition from fourth orbit to second orbit in a hydrogen atom? Can we calculate this value easily?
Yes, sir. In place of NF, we substitute 4.
In place of NF, we substitute
2 and NI, we substitute 4.
So this will always be smaller number, then only it will come positive. A smaller number comes here and larger number will come here. The reverse, is it not? So this final value comes here. This value always be smaller, then only emission will take place. So we can calculate energy of emission for any hydrogen-like atom for any transition by suitable substitution. And energy will come in terms of electron volts. This also sees. For hydrogen spectrum, everything is at equal to 1. And there are 5 common series you are familiar with. I will not spend too much of time. How do we define those series? Those series, see what we notice here, what is common in this case? All these arrows are part of Lyman series. What is common in all such cases? Okay, also just a second. Hello? Hello? But right now I'm in the class, can you call later? Maybe after 12:40 or so? After 12:40, yeah, okay. Okay, thank you. Okay. So when we look at this entire thing is called Lyman series. What is common in Lyman series? They are all terminating at a common place. What we notice here, Lyman series correspond to it is final. This is something, finally it is transitioning to ground state, or NF is equal to 1. So all series are based on the final orbital to which electron is transitioning to. So this is final common series based on final value of N. If N is equal to 1 is Lyman series, N is equal to 2 is Barman, Paschen, bracket and 1. So corresponding value of N we can easily understand. Now when we have N is equal to 1, see this is something it can transition to N is equal to 1 from 2, 3, 4, 5, 6 and up to infinity. So we know for Lyman series, which of the transition will have lowest energy? this will have lowest energy. The lowest energy is corresponding to transition from next higher level to that level, and highest energy corresponding to infinity to that level. Okay, so we get a range of energy for Lyman series, and once we get the range of frequency, and we get the range of wavelength as well. And what is Barman series? And Barman series is the one which is more popular. You notice here Barman series, what is the transition from here to here? What is the energy gap? So when it transitions from n is equal to 3 to n is equal to 2 in case of hydrogen, it will emit a radiation corresponding to 3 power 4 minus 1.5. What is 3.4 minus 1.5 is equal to? Is roughly 1.9 electron volts. And 1.9 electron volts correspond to red color, and the minimum energy level of visible spectrum. And as it transition from n is equal to 4 to 2, energy is little higher. It is green, blue, violet, and all. So the Barman series, you see visible light falls into which range? Roughly, as we said, it forms into 1.8 electron volts to roughly 3.2 electron volts. So here what we notice in case of Lyman series, everything is in ultraviolet and easy to understand. This is the lowest energy of any emission in Lyman series. This is the lowest state. You understand what is the lowest state is transitioning from, if final n is 1, so lowest is from 2 to 1. For Barman series, the lowest energy will be from 3 to 2. For Paschen series, lowest energy will be from 4 to 3. So next higher to that state, and so on and so forth. So in this case, lowest energy is from this level to this level. What is the difference from here? Difference is 13.6 minus 3.4, which is 10.2. So 10.2 is minimum energy of emission in Lyman series. Rest all even higher. So none of them are visible spectrum. So if hydrogen atom emits radiation falling into Lyman series, we cannot observe. It is not visible. Whereas in case of Barman series, yes, even the lowest energy radiation, reddish color, next higher level, greenish shade, bluish shade, and so on and so forth. And what will happen to the greatest energy in the Barman series? You transition from close to infinity to this level. What will be the energy level of this photon? It will be roughly 3.4 electrons. And 3.4 is again outside the visible spectrum. So here also we get only few radiations which are outside visible spectrum, but it gets number of radiation which are falling within visible spectrum. What happens in case of Paschen series? In case of Paschen series, even the maximum energy of any radiation in Paschen series will come from here to here. When it transitions from here, 0 to minus 1.5, so maybe in terms of sign, we take reverse. Loss is equal to 1.5. And this also is falling in infrared region. So this is not visible because it is falling in infrared region. This is not visible, it is falling in ultraviolet region. This is visible because it is falling in visible range. So you understand three things we need to understand. So we define series Lyman, Barman, Paschen, bracket, and fund based on the value of NF, final destination, which orbit it falls to. If n is equal to 1, Lyman, 2 is equal to Barman, 3 is equal to Paschen, 4 is equal to bracket, and 5 is equal to fund. And within this each also, there's a range of energy. And once we find the range of energy, we can find the range of frequency and range of wavelength also. The lowest range will correspond to minimum difference in n. In case of minimum range, whether this will be ni will be just higher by one number. That's minimum energy gap. And maximum energy gap correspond to ni is equal to infinity. Okay, that's the 2 points we need to understand. First line of the series, transition from next higher state. Hence minimum energy or maximum wavelength. So this radiation will lead to maximum wavelength corresponding to Lyman series. And last line of the series is maximum energy. And maximum energy is minimum wavelength. From where? This will be equal to lambda min for Lyman series. Similarly, this is equal to lambda max, and this is equal to here lambda min will come like this for Barman series. So I hope you understand what is the first line of a series. First of understanding series. Okay, first understanding emission. As emission is because it moves from higher energy state to lower energy state. So whatever is the energy difference, it loses energy in form of EM radiation. It's like emits photon. So each transition leads to emission of one photon. Okay. Second thing we understand what we call them series in case of hydrogen atom. This series also we have to understand. Series is based on fine NF orbital. Which orbital finally it ends up in? That is in the destination orbital. and first line corresponding to minimum energy, and last line corresponding to maximum energy. Minimum energy from next higher orbital, maximum energy from infinity to that orbital. Dhanshri, is this clear so far? Kaushik?
Yes, sir.
Is clear?
Yes, sir.
So far you are clear. So what you have done so far, one is calculated radius, energy, and velocity of any orbital electron. And now we are talking about emission spectrum. What are the different series? What is the first line of the series? What is the last line of series? And these are 4 or 5 points we have done. And you would have done the same thing in chemistry as well, which should make it easy for you to understand. Okay. Now we'll do some more. First, we'll try to understand Bohr model better. So let's see this one, but we'll do some couple of questions which have come in the past, which are application of Bohr's model. What is application of Bohr's model? Bohr's model, in addition to circular motion, we have one more equation. That one more equation is mvr is equal to nh by 2 pi, and that can be applied in several hypothetical scenarios. That's why let's lead this question. If one were to apply, what does it imply? It is not truly valid. But if we assume it was to be valid, if Bohr's models were valid, in case of electron moving in a circular orbit under the influence of magnetic field, what will the energy of charged particle in the nth level? Now, this is the question. How do we solve? So this question also, let's say, whenever we come across Bohr's model, there are 2 things which are valid. One is orbital motion. In case of orbital motion, it is undergoing circular motion. The centripetal force has to be equal to some force acting. In this case, it is EBB or QEB. Okay, if charge Q is moving, you can written QEB. And in that case, the radius is equal to mv by qb. We know already. But what is the additional equation? This is one equation. What is the second equation I can write now? The second equation I can write is Bohr's model. mvr is equal to nh by 2 pi. So what we need to calculate, I need to calculate energy of the charged particle in the nth level. Okay, and let's suppose in this case, how would you calculate energy of the charged particle? Basically, in this case, in case of magnetic field, there's no potential energy. We have to calculate kinetic energy. So when I have to calculate kinetic energy, what do I need to do from these 2 equations? Can you think of a method how to solve this one? What do I need to do from these 2 equations? First, you want to understand when you talk about energy of charged particle in the nth level. See, when it is moving under influence of, see, it is something like this. You have done as a field is something like this. The charged particle is moving. Uniform field, it goes into circular path. It has only kinetic energy. There's no potential energy associated with this. So, what will the kinetic energy in this case? How would you calculate kinetic energy here? I have to calculate velocity. How would I calculate velocity? By eliminating r to obtain v. Okay, so we substitute value of whichever equation we take, we eliminate r, and r from this equation is r is equal to mv by qb. We substitute in this equation, we get a value of v. Once we have value of k, we can calculate kinetic energy, which is equal to 1 by 2 mv square. Okay. So I hope this is something all of you can easily do. Similar question is like this. Again, think for a minute, exactly similar approach. This question also has come in several competitive examinations in the past. And this also again hypothetical case. If we assume only gravitational force. The previous case, which force was causing circular motion? Magnetic force in case of gravitational force. If we apply Bohr's law, find the expression of ground state energy of an atom.
Sir?
Yes?
But here you have to consider potential energy also, right?
Yes, in this case, we have to consider potential energy. What will the ground state energy? Suppose I calculate kinetic energy. From kinetic energy, can I obtain ground state energy? What is the ground state energy? See, if I calculate m by 2 mv square, that is my kinetic energy. I have calculated kinetic energy. How do I calculate ground state energy? Is ground state energy is total energy? Is total energy related to kinetic energy?
Negative.
Negative of that. So it is equivalent to, when I say ground state energy, actually this is nothing but negative of kinetic energy. And that's why first thing I noticed, yes, this option is out. This option is positive. Energy has to be negative. And this is something we see in case of gravitation also. So this question also is similar to finding velocity. And after finding velocity, I calculate kinetic energy and put a negative sign. That becomes my ground state energy. Can we easily solve? What is the method? Two equations. Which are the two equations? One is orbital motion. mv square by r is equal to gravitational force of attraction. Two masses. Which are the two masses here? Mass m and m, mass of proton and mass of electron. And we are ignoring here. This is a only gravitational force attracts. Force is acting. Hence, we have not written Coulomb's force. This is one equation. Second equation, Bohr's model. mRV is equal to nh by 2 pi. Again, what we do, we calculate velocity. Once we calculate velocity, I can easily calculate. So either I can calculate velocity, sometimes if radius is given, I can calculate radius also. There are two ways of, I am just for the sake of doing a different way. One way I can, similar to previous question, I can calculate velocity and calculate kinetic energy. What is the other way of calculating? Other way I can calculate R and then calculate potential energy. If I calculate R, what will the potential energy be equal to? If I calculate the radius of orbital motion in ground state, what will the radius of motion, radius in the ground state? Corresponding to n is equal to 1. For n is equal to 1, if I calculate radius, what will the potential energy in that case? This is potential energy. So if I calculate R also, I can obtain potential energy. And what will the total energy in that case be equal to? Minus P by 2. So you understand both ways it can be calculated. One way is calculation in terms of you calculate velocity by eliminating R. I can also eliminate V, obtain the radius. After obtaining the radius, I can use this expression also. If I obtain this radius, it will be equal to minus 1 by 2 G into M by R. I can substitute this R value in this equation also, and you can easily get an expression. Ravni?
Yes, sir.
Have you understood? Can you solve this question?
Yes, sir.
Here. So any case, whenever you come across what is Bohr's model, two equation, two unknowns are R and V. Depending on whether we want R or V, eliminate one, we get the other one, and we can solve. And I hope this part also is clear how three terms are related. Which are the three terms in case of gravitational force and in case of Coulomb's force? Three energy terms are total energy, potential energy, and kinetic energy. And relationship between the three should be well understood. You can easily solve. Ground state energy, either that way, or either I can form from this method or from this method. Any way you can solve. Okay, this is a slightly different one. Imagine a particle has charge equal to electron and mass is 100 times the mass of electron. It moves a circular orbit around a nucleus of 4e. And then we have to calculate expression of radius in nth orbit. Suppose, I'll come to these questions later, but suppose I have to find the radius of nth orbit. How would I calculate radius of nth orbit from this question? How would I calculate radius of nth orbit? Using which law? Bohr's law. How many can calculate radius of nth orbit here?
Sir,
Advay? Yes?
sir, if mass is infinite, gravitational force will also be there.
No, the mass is okay. See, yes, in a way you are right. Okay, this is something energy pass an electron, Bohr's model to be applicable. What it assumes here, see this, you look at this expression here. See, who said this? Halat?
Yes, sir.
Okay. Tell me, what you say, I don't deny. But this question, I will not worry about this. Why would I not worry? Tell me. Why would I? Yes, you say if mass is infinite, it means gravitational force also may be infinite. But that question will not, it should not affect my solution. Why should it not affect my solution? Can you notice something? Why should not I bother about this? Vignesh, you have this problem? You also feel this is a issue here?
In this question, sir?
Yes?
Maybe not, sir.
Why not?
I'm thinking.
Think of why not. And see, look at the options. See, what he says, I don't deny. Okay, this gravitational force, this question, and this kind of question have come in the examination. What it assumes here, Bohr's model applicable, it assumes that we ignore, they have not mentioned here, but options given here do not have G term. So basically, though it is not mentioned, what you have to measure in case of when we calculate, even when you apply Bohr's model to orbital motion of hydrogen atom, other atom also, what we do, we don't write gravitational force. Why don't we write a gravitational force? In case of proton and electron, the electrostatic force is much larger than gravitational force. Okay, so we ignore. So perhaps what should I take as the mass of the nucleus to be much greater than mass of electron? That would have been the right wording. And here options do not have gravitational constant. So it means they are ignoring gravitational force. And is there a logical reason why should we ignore gravitational force? Can someone think? I think I mentioned once earlier, maybe some time back. Why can you give a reason why gravitational force can be ignored in case of what are things involved? Nucleus has protons. It has Z number of protons, and there's an electron here. So there's a electrostatic force and there's a gravitational force. Why can I ignore gravitational force?
It's very small in
If
comparison.
you calculate here, depending on this gravitation, this constant, we can calculate this is thousands of times larger compared to gravitational force, hence we can ignore. So right, so this is something we can ignore. Two reasons I can ignore. What are two reasons I can ignore? In the options, very clearly, options do not include the G term. So options, you give me a clear hint that I need not worry about gravitational force. And second thing, here also involves basic particles, proton and electron. And whenever these things involve, gravitational force are negligible compared to electrostatic force. Okay, so come back to the same question. How do we go about solving it? Again, we notice here it is based on Bohr's model. More as a Bohr's model, I write two equations. Which are two equations I write? Orbital motion. This is the equation, first equation. And what is the second equation? What is M here? See, only change in case of hydrogen atom model. What is the difference in this equation compared to normal hydrogen-like atom? Can anybody spot what is the difference here? This equation, is it any different from equation we write in case of hydrogen-like atom? What is the difference here?
Z term.
Because this M is not mass of, then when you write equation, this term is actually mass of electron. Here this mass is not electron, this equality, this M will be, M is nothing but, here this M is equal to 100 ME. And that's all, this M only, but this is what we have to understand. This mass which is orbiting is 100 times more than mass of electron, which is a normal case in case of an atom. But equations are same, method is same. Only thing, this mass will be different, hence the radius will come different. Okay, this equation is, are you following, all of you following this point? Gayatri, have you understood what I said just now?
Not clearly, sir.
Not clearly, okay. Where from this equation has come? Why you written this equation? Are you seeing this, Gayatri, this equation first time? You seen it before?
Before, sir.
Huh? This equation? So what is this equation? Where from this equation comes? What is orbiting here? Let's understand again. What is orbiting here? There's a nucleus which has charge equal to 4 electron, and there's an orbiting, and this is okay. And what is orbiting? This is charge is equal to E, but mass is 100 ME. So what has happened? Unlike normal electron in orbital motion, this is an hypothetical object which has charge equal to charge of electron, but mass is 100 ME. So when I write this equation, basic equation I'm writing, electrostatic force of attraction is equal to centripetal force. When it writes centripetal force is mass of orbiting object V square by R. This M, what is this M implies here? This M implies mass of the orbiting object. And what orbiting object, what is mass it has? It has mass equal to 100 times mass of electron. That's the only difference. And what is second equation I write? Second equation is normal Bohr's model. How do I find the radius now? Gayatri, can you tell me what I need to find? I need to find the value of R as a function of N. How would I find the value of, that's fine, I have to find the radius. How would I find the radius from this expression, Gayatri? There's two equations are given. What I need to get here? I need to get the value of R, expression of radius in nth orbit, in terms of N. How would I find R here? Not sure, Gayatri?
No, sir.
No, okay. If we ask somebody else, then Tejas I. Can you find R here? How do you find R here? How do you find this value of R, Tejas? Not clear? Pranav Soma? Pranav?
Yes.
How do you find the value of R?
MV by QV.
Okay, so not so. Okay, Preetham, how do you calculate R?
Yes, sir. We use that n square h square epsilon naught by pi mz square.
Pretty simple. I think I have repeated this. I think if you go previous slide, I've mentioned 3 times to find R. See, this expression doesn't have V. I have to eliminate V to obtain R. How do I eliminate V? This equation, from one equation, substitute V value in the other equation, you get the value of R. The method of finding of R is eliminate V. This equation, 2 equations have 2 unknowns, V and R. So we substitute value of V from one equation to other, you get the value of R. As simple as that. Okay, so that's the way to find. So and eliminate V from obtained radius. So what he had done, this equation, I have to put the V value from this equation to this equation. So M by R, V value is what? V value is NH by 2 pi by MR whole square. So N square, H square, this term is equal to this expression here. So what we get from here, so this, when you look at this, RR gets cancelled. We get an expression of R. And if you compare this R, only thing different in this expression, see, if we take hydrogen atom, this M is equal to Me. Now, in this case, this term is 100 Me. In the denominator, compared to normal hydrogen atom, I get a term which is 100 times. This term is divided by 100. So the radius of such an imaginary atom, will be 1 by 100 times of corresponding normal atom. So if I had a, okay, so this whole term, what is N written here? This mass here is N times mass of Me. And if I write the whole term, this term is equivalent to, rest of terms are common. This is equal to 0.53 N square by Nz. So the radius will become 100 times smaller than the corresponding radius of an atom which had 4 protons and had an electron which is orbiting. Compared to that, radius is 100 times smaller. So what is the expression you get? Okay, this is something further I'm going into this, but if you substitute this term here, if this N is 100, and what is the expression we get here? Z is equal to 4. This expression is simple, that I'm going into further explanation. To write this answer, if I substitute N is equal to 100 and Z is equal to 4, this term 400 and this expression. So Gayatri, was it difficult?
No, sir.
2 equation. Every time, what are we doing here? 2 equation. Which are the 2 unknowns? V and R. So depending on whether we have to find V or R, we eliminate one and we get the other. As simple as that. That's the basis of Bohr's model. So anything, any variation of standard Bohr model, we have to solve. That's the one standard way of solving. Okay. So we have completed. Okay, I'll stop here. I think it's already a bit overshot. And we'll do some more numericals in the work session afterwards.
Sir?
Yes?
In case of the magnetic field,